What's going on, you guys? Cameron here. So basically what I want to do is talk about what I'm doing as far as a project as my full-time job now. Basically, this is going to be a channel about how to not only the starting blocks of growing a hardware slash software company that works together for the screen printing industry. So my background is screen printing. I did screen printing in high school. It's something that I started in the middle school, but then I actually created a screen printing business when I got to high school. And I started out of a 10 by 20 foot shipping container. And with that said, you only have so much space. And behind me here is a manual screen printing press where you can screen print t-shirts up to 4 colors, like the shirt I have here is 2 colors, and you do that process with screen printing. And it's a very tedious, long process of using something like a squeegee, like I have here. This is a custom-made frame, but this durometer, the 70 durometer rubber part of the squeegee, is what's used to flood the ink and print the ink through the screen onto the shirt. And there's other options other than having manual screen printing presses. There are automatic screen printing presses that you just load the shirt and the machine will rotate the shirt to go to the appropriate screen head. The screen comes down and then it does the flooding and printing for you. And basically what I want to do is create this desktop type hardware that can go on top of your manual screen printing press, on top of the screen, in the same footprint of a manual screen printing press, and do the manual the flooding and printing for you. So you pull the screen down, click a button, and it does the flooding and printing for you. I think that would be super cool, be super compact, and efficient for manual print shops. If it can be the same amount of time, maybe faster, and if it can give you the automatic printing quality on a manual press, meaning that from shirt 1 to shirt 1000, your consistency is exactly the same. Your pressure, your PSI pressure going through pneumatic cylinders is exactly the same, so that every single screen from shirt 1 to shirt 1000 is printed exactly the same. I think that would be super efficient and a cool thing to look into to see if it's even feasible. I know something like this for one color jobs will be amazing, because it's just going to be, I think it'd be a lot faster, especially on one color jobs, because you're just pulling the screen down, and that initial time to reach for the squeegee, that initial time of flooding and printing, you kind of change it up as time goes through. So with this, it stays more consistent, and usually when you create a better consistency to an operation, speed actually increases. So with that said, that's basically what I do here. I got 3 3D printers. Actually, I have 4 3D printers. 3 of them are just the traditional type 3D printer, and then I have the 4th 3D printer I have is a belt 3D printer. That's a little harder to use, so I don't really consider it a 3D printer. And then I have a CNC desktop machine. It has an 8x8 platform where I can CNC stuff out of stuff like aluminum. And then I have a sander. I have over here a little bench top lathe. I got a scroll saw. I got a bandsaw. I got a metal chop saw. And then over in this corner over here, I have like electronics, mainly for a soldering station, microscope, stuff like that. And then I have a bunch of hand tools from Ryobi and miscellaneous stuff like wrenches and all that stuff. So that's basically the shop, and basically with all those tools that I have here, I've been able to build the current version. And basically what I want to do is go through everything that I've actually built in the last couple months, and pretty much we don't need to talk to spam callers today. And pretty much go through almost every component and basically how I got to this point and where I'm heading. And basically how do you go from prototype to product? How do you do this process? I don't think I have the correct answers. I don't have the only answers. I just have what I know is working. So basically, most of my prototypes started out with 3D printing. That's basically where I started. I have a bunch of 3D printed parts that didn't work, and I have a bunch of 3D printed parts that did work. And basically, this is just helping me prove the concept of what I'm trying to build, making sure that it's buildable, and making sure that all of these components can come together and work the way I want it to. So, all of these 3D printed parts that I made here, this was the main driver. So this part here connects together and holds the pneumatics, and this actually allows the pneumatics to roll on the actual chassis of the aluminum 8020 T-slot aluminum extrusion. So this slides with bearings across while holding pneumatic cylinders. So that's what those are for, and that proved the concept with connecting a rubber belt to a stepper motor and looping it around a 8020 aluminum extrusion to see if I can put, let's say, 30 pounds of pressure downward force with the pneumatics. And basically what that allowed is that we had that 30-pound resistance, and I wanted to know, can a rubber belt and a servo motor, or I'm sorry, stepper motor, be able to pull that torque resistance? And what I found out was that the normal NEMA 17 motor didn't have enough power, but what I did do is I did some calculations on a gear ratio that will allow for a 18-to-1 gear ratio reduction. So now, when you do a gear ratio like that, you lower your speed down, but you increase your torque, which is what I needed to be able to pull that amount of force from one side of the screen to the other. So that was a cool test. That worked out great. Some of these other things I got are like brackets, height adjustment brackets, to where you can take the full chassis and lower it or rise it according to your press. Then I got some stepper motor holders that this will literally just bolt to the top of this extrusion, and the stepper motor just sits right on top here, and it has a little pulley that the rubber belt wraps around, and it will pull the main driver or push it. So that worked out very well. And then we got some servo motors. Servo motors are for my squeegee here, and the squeegee will have a bracket on one end. It actually slides onto a secondary bracket, and that bracket's connected to the servo motor, and this allows my squeegee to change angle based off of if I'm flooding or printing. So we got some servo motors on that. We got the squeegee frame, and then we got some solenoids. So these help direct airflow. If I want the pneumatics to go outwards or inwards, I can direct that airflow for a two-way pneumatic. These are 5-ported pneumatics, so you have air in, you have 2 exhaust ports, and then you have 2 exit ports, basically output ports. That's a solenoid. And I got some more brackets for holding up the secondary height adjustment bracket. They actually, both the servo motor bracket actually holds up the front height adjustment bracket, as well as hold the stepper motor. And then I got basically some slots for bolts to slide into the 8020 aluminum extrusion. And basically this just bolts down, cinches against that T-slot, and holds it in place. We got some mufflers. These mufflers allow you to control the flow rate, the exit flow rate of the air coming out of the solenoid. So if you want air to come out really fast, you open these all the way up. If you want the air to come out slow, meaning that if it takes a longer period of time for the air to escape, that means when your rod in your pneumatic is going up, it has a little bit of resistance because it can't get the air out. So these are mufflers. You use that for controlling the airflow coming out. Now I got some knobs for my sliders, because what I end up having is a square tubing here where these sliders will slide onto the square tubing, and you can slide it inward or outward to change the size of your squeegee frame. This is a 16-inch squeegee frame, and we're gonna have the 4-inch, 6-inch, 8-inch, 10-inch, 12-inch, 14-inch, and then the 16-inch for starters. So we got those. And then I got a U-bracket. This U-bracket helps to basically cup under the main driver. So basically this piece that slides with the pneumatics, this has to basically do a U-turn underneath the bearing so that when this comes up, it doesn't hit nothing. It actually touches right now because what I need to do for the testing at the time, I had to shorten this. This used to be a lot longer, and I shortened it because I didn't have enough space with these height adjustment brackets. So these are considered 6-inch adjustment, and I think on my press I need like a 7-inch adjustment. So every press will have a different height adjustment bracket depending on what brand press you have. So we got to figure out the math on a chart that says, okay, if your screen is, let's say, 4 inches away from your top knob bracket on your C-clamp, then you're going to need a 6-inch height adjustment bracket. So those things we're going to figure out down the line. And then we got some limit switches. This will tell the computer saying, hey, when the main driver is coming and it bumps the front limit switch, stop and go through the print sequence. So usually you would flood, hit the front one, stop flooding, flood pneumatic, so the pneumatics will go up, the squeegee will change angle, and now it's going to go backwards to do a print. So the pneumatics will go down and it will print, and then it'll hit the back limit switch. That will be considered a print sequence. So that's basically those components there. And then getting into more of the off-the-shelf parts. Some of this is off-the-shelf and some of it's custom. Most of this here is like the valves, the nuts, the bolts, the brackets. But a lot of this gray stuff here is all custom made that typically I couldn't find off the shelf based off of my size constraints and my weight constraints that I wanted. Now we're getting into the motherboard, or I'm sorry, the touchscreen device. This is a 7-inch capacitive touchscreen, so it's similar to like the iPhone touchscreens or your Galaxy touchscreens. And yeah, this is going to be really fun to play with. It's a complete board for controlling the graphics and the touch input. It's 7 inches. It's really nice. This is just the board and screen. There's no housing to it because I feel that I might need to custom build that. So I've already went ahead and I purchased 4 of these already. So I have 4 touchscreens. So now we're all into the Nexten. I think these are called Nexten. Yeah, Nexten Tech touchscreens. So I got 4 of these because I have a 4-color press. So we're going to go through the process of making sure everything works on my press as a full unit. So I already proved the concept on using 1 unit by itself. With that test, I do have some modifications that I want to run. And basically what I'm going to do is I'm going to push that modification to production. I'm not going to just sit at 1 unit because I need to get the production part figured out at the same time, so that hopefully at the end of it, while building most of the components that aren't changing, that they're pretty much locked in, that will tell me, okay, production needs to run this way with this part. This part takes this long to build. And that includes stuff like cutting the 80/20 aluminum extrusion, like getting a 10-foot piece and cutting down to 24 inches. How long does it take to build a 4-unit press? Or how long does each one of these 24-inch pieces take to actually measure out and cut? Now there's ways to optimization on building jigs and custom templates so that you don't have to constantly measure. It's just butt up the material, cut. Butt up the material, cut. And then I can also buy like 2 10-foot pieces or 4 10-foot pieces and combine them together, and then I can cut like 4 at a time. So there's ways for optimization, but until you start that production round of building multiple units, you won't know that until that comes. So that's the touchscreen display. I just showed that I have 4 24-inch aluminum extrusions. These are 30 millimeters. And then we got some other components like some L brackets. This is what allows the whole unit to sit on the screen. So I got 8 of these cut up. I still have to drill the center hole, but I am changing the design on the height adjustment bracket so that instead of having 1 bolt at the bottom, there's going to be 2 bolts. Because what happened was that this started to sway even with a lock nut, so it's not strong enough. So that definitely needs 2 bolts to keep the swaying away. And then we got, this is actually not a part of this, it's this size. We got some square tubing. This is basically what stays mounted to the pneumatics. And this little bracket here, this U bracket, bolts on top. Haven't decided, I might end up welding that piece with tail welding. We're gonna machine probably this U bracket out of aluminum so that this is a full unibody aluminum piece that connects to the brackets, or I'm sorry, the pneumatics. And this whole frame will always go up and down. And basically all we gotta do is put these slide brackets on, and these slide brackets will slide along this bar so you can change the size of your squeegee. And at the top are going to be some, we just had them, it's going to be those knobs that we talked about, and these knobs allow you to just tighten down against the square tubing, which will be really cool. So that, for the most part, that concept worked. The only thing that I want to change is the side brackets put the squeegee in front, puts the squeegee in front of the square tubing, and it rotates in front, but most of the pressure is right underneath this. So what I'm going to do is change these brackets to where the squeegee is directly under, and I didn't do it for the test because I had height clearance issues, and I have a feeling that I can quickly fix that with just taller height adjustment brackets. So for the next test for all the units, we're gonna just jump to basically manufacturing based off of what I think I need, and we'll go from there. So I do have to modify these. The height adjustment brackets are easy to modify because it's parametric design. It's very easy to just go in there, type in the height I want, and it will automatically change the whole design to what I need. So there's that. I've already started manufacturing aluminum main drivers. I changed the design slightly so it's manufacturable, meaning that when I was 3D printing this, it was off just what I wanted to design, and like the look and feel for a 3D printer, and quickness and strength for a 3D printer. And for the most part, the concept's the same. So this is the 3D printed one, and this is a CNC machine one out of aluminum. And basically, since aluminum's stronger, you can get away with a lot less material. And the fact that this piece here would need to be machined pretty much in all 4 directions. So you'd have to machine the top, then you have to flip it on its side, machine that top, flip it over, machine the bottom, and then flip it over and machine the back. And that's just way too much work. It's a lot of machine time. So it's like, how do you get that machine time down so that you can get it done in a reasonable amount of time, but don't cost strength of material, don't cost weight of the material. And basically this is what we came up with. It's a slotted design, it's a 2-piece design. So you mill out the back plate, and then you mill out this flat plate here, and this flat plate has a slot down the middle that we just hammer this piece in, and then we're going to do some TIG welding lines on the back to keep that part from slipping out. So basically I made 8 of these. I've assembled one already, but I took it apart because I don't have a TIG welder. I'm working with a family friend of ours to TIG weld these backs, and I'll do the full assembly soon. But I have a video that I'll play where I show it sliding really nicely on the aluminum extrusion. So I think I got the production part of how to manufacture these down. And to be honest, it takes a while. It takes about 2 hours to machine full 4 units on the CNC machine. So I mean, 2 hours is not that bad, but when you think about, like, that's only for 8 separate pieces for 4 pairs. Imagine 100 of that. I mean, that's a lot of hours. So the cool thing with this flat design is that we can easily put this in a water jet, and a water jet will just rip through aluminum way quicker than a end mill would. So looking at water jet pricing for what this would cost me to, say, make 10 pairs or 10 units or 20 pairs and stuff like that. So I found that water jetting is a lot cheaper. And then we're working towards some printed circuit boards. And this is cool because this was the first iteration based off of components that I could buy off the shelf right now. With coronavirus impacting the global economy on basically the chain, the logistics of getting supplies. We have a lot of ports full right now. Ships can't dock and they can't unload. So based off the components that I could buy right now, I opted to build a single unit motherboard for each unit. So each unit will have its own computer for my original testing. I do have a main logic board, one board that will control all 4 units, but those components are going to take about 30 days to come in. I'm working with PCBWay. They're manufacturing the boards, and they're going to fully assemble the main logic board for me. Every single unit will still have a small board. The small board will handle all the individual plugs for each individual component, like the servo motor, solenoid, and the stepper motor. So basically all those components plug into a small board, and then from the small board we take one cable and we plug it into the main board. That allows for an easy disconnect so you can take the unit off your press. But for now, like I said, I want to get the programming in order, I want to get the touchscreens in order, and these small boards will allow me to do that. And basically what the small board has is, we got these jack pins here, which will actually allow for our microcontroller to sit on. So we got that. I don't have all the components out, but this will give you an idea, basically what we're looking at. So you can see how I just have this blue one right here, this semi-big one. This is Arduino, it's an Arduino Nano. Basically just a little computer chip where you can upload a program and put power to it and basically just run the entire operations of the board, which is pretty cool. And then we got a stepper motor driver. This controls the logic going to the stepper motor, so you're constantly switching the stepper motor on and off. That handles that. And then what I would like to test out, I put a basically an accelerometer / oscilloscope, or I think it's an oscilloscope. I think I'm butchering that one. Accelerometer and gyroscope. I'm sorry, gyroscope. Accelerometer and gyroscope. Those allow for, like your cell phone, when you go to portrait to landscape mode, your phone knows, hey, you're in landscape mode, switch the screen around. I'm adding one of those chips for an idea of possibly testing the idea for the software to know when your screen is lifted and lowered. This will help with efficiency. It will collect data. It will tell you how long it takes you to lift a screen up. It will tell you how long to put the screen down. And this data collection will help us figure out how long a job take for us to complete, based off of like, oh, you got 1,000 shirts to do or 300 shirts to do front and back. As the machine is collecting data, it can actually tell you an ETA when you're going to be complete with this job if you stay in that consistent manner. This is where algorithms come in and data collection. This board specifically can't collect data per se because there's no SD card, but we'll figure out how to collect data probably through the Bluetooth module on it to send data to a server or something like that. For now, the main logic board that I was talking about earlier will have an SD card, so all of the data that you're generating will get stored on that SD card only. The SD card slot will also act as a upgrade mechanism for the firmware. So instead of having internet on the board, you'll have Wi-Fi on the board, but I don't think you're going to be able to surf the web because of the logic board that we got to develop. But you can use another computer, download and update software, save it to an SD card, and then plug the SD card into the main board, and it will automatically detect that and update the software for you. That's for that. And then basically just have some wire here, and I got some capacitors. And basically that's just gonna help me get the development board for a single unit developed up, soldered up, so I can start programming the touch screen. This will help me start making sure all the components are working together on a printed circuit board. I do think I should have probably tested this out 100% before ordering the logic board, because the logic boards are pretty expensive to order. But it is what it is. I feel pretty confident in the guy that I had designed the printed circuit board. So we just gotta play the waiting game right now. We're just waiting on those components. The only other thing that I feel that we need to work on is different mounting system for the squeegee, and also different design for the squeegee, because this is where I'm like between a rock and a hard place on deciding, like, okay, do I stick with this design? Because if I stick with it, then I don't have to make too many changes to the side mounts and the servo axle. It's a little clunky that I don't like. That's why I kind of want to fix it just a little bit better, so it feels more confident in how you connect and disconnect a squeegee frame. I can make this really easy on a 3D printer. It doesn't look the prettiest. I think I know how to make it pretty with some sheet metal wrapping around. That will also give it an additional strength. But again, the mounting mechanism is not the most ideal solution. I think I need to refine that design a little bit better. So I'm gonna play with some ideas, maybe do some iterations in between production. Other than that, the current design can't really be machined out of aluminum. It's possible that it could be injection molding, but injection molding is very expensive because we have to basically order a specific amount of quantity because you're ordering the mold, and the mold is the most expensive part. But once you have the mold, you can basically just get as many units as you want when you need to. So there's that possibility, or the 3D printing possibility of just 3D printing these. The 3D printer, for the belt 3D printer, can put this out, put a whole squeegee out in about 12 hours. That's with no modifications to the settings, optimization to the settings. I feel that we can increase the speed probably a little bit. Also, this is like a 0.4 millimeter nozzle, and basically with that, I can actually increase the nozzle to like 0.8, and that will cut down the time it takes to manufacture this down already to 6 hours. So there's ways to optimization there that we'll definitely take a look at. But yeah, what I'm working on next is making the height adjustment brackets out of aluminum, CNCing those out of aluminum. I got to redesign the side brackets. Once I need to design them also around this idea of manufacturing them and not just be 3D printed. There's a different process there. So I gotta fix some of the designs for manufacturing, get the manufacturing in order. I finally got the CNC machine dialed in the way it can just quickly put in material, program the machine, and it just cuts without stopping, stalling, or jamming up. So yeah, I'll also end up, when I have some downtime, I'll solder up these main logic boards so that if stuff is making on machines while that's going on, I can start plugging in these motherboards, the touchscreen boards, and start programming the interface, programming the logic logic gates for 1 unit, 2 units, 3 units, 4 units, so that all work together seamlessly. So that was a rant on basically an update of EzPress. I thank everyone for watching. This is not just for screen printers. It's out there. This is out there for anyone that wants to build hardware and software and build a product and bring it to market for whatever industry that you're looking to build for. I don't have all the answers, but I have some answers that have worked for me, and then I'm just going to keep going with on that. And if you have an opinion, if you have any insight on what I'm doing wrong that I can improve on my production side, that'd be great. Leave a comment down below, like the video up, ask a question about your project. I might be able to help you. I use Fusion 360. I use Eagle for PCB design. I have a click and print 3D printer, which just uses the slicer program for slicing the STL files. I have a Creator Pro, an Ender 3 Pro, and the Ender belt printer, the Creality belt printer. Now I have the Nomad CNC machine. I don't know if they have a Nomad. I would consider it the Nomad 2. So Nomad 2 CNC desktop machine. It's an 8x8. I use Fusion Cam to design all of the aluminum G-code to cut out the part on the machine. And I got mainly all of my hand tools are Ryobi. I got the Harbor Freight mini lathe, and I got the Porto Cable metal chop saw. And for the most part, that's basically the tools that I use. So if you have questions about those, like I said, you can email me at ezpressplus@gmail.com. It's the letter ezpressplus@gmail.com. And you can comment down on this video. I'll respond to that. And yeah, guys, thanks for watching. And until next time, peace out.